Well, thanks for being here, and thanks to the organizer at the Newton Institute for the invitation. It's great to spend 3 months here. And the work I will describe right now was actually defined and developed at the Naval Postgraduate School while I was visiting Frank and his group through an Office of Naval Research Global grant. So I would like to acknowledge their support. I was a student at Barcelona Supercomputing Center with my supervisor, Mariano Vasquez, and I will defend my thesis in a few weeks. You're probably here because of a certain title that you saw on the calendar. The title is not quite the same because, well, thanks to some discussion with Mark Taylor yesterday, unless I had put some more explanation on that title, it could have been a little bit misleading on what I meant. So I rather I changed the title to more something about stabilization of spectral elements and see how we can reach a quasi-monotonic solution of the advection diffusion equation using a variational multiscale and some help to it. So the idea is that of trying to avoid this type of problems. So oscillations not only close to a discontinuity. In this case, we are transporting a square wave on an infinitely long channel. It's a square wave in 2 dimensions here. I'm just showing you the slice and using some filter. Filter, in this case, we haven't really played with the filter too much. We didn't really think about how to tune it to get a proper solution. For mainly, we wanted to see how just applying any type of filter, how that would behave. And also, eventually, we would like to have some stabilization technique that does not rely on any type of user-defined parameter and tuning technique. So if we simply use a filter on this on a discontinuous problem like that, what we observe is not that we simply have discontinuities under and overshoot at the discontinuity height, but also where the solution should be smooth. So we might have some oscillations that we don't like. And how could we kill those oscillations? Maybe by using artificial diffusion. Yes, we kill all the oscillations, but we also kill the solution. The square wave is not square anymore, so we are paying a great fee just for using some maybe simpler technique than a filter, but that is not still able to give an accurate solution. So maybe something in between could be using hyperviscosity. Hyperviscosity, it is in this something between a filter and artificial diffusion. In terms of accuracy, we still have some oscillations that we wouldn't like to have, at least in terms of under and overshoots. But definitely the solution is more controlled. Far away from the discontinuity, the solution is smooth. Nevertheless, probably this is not as good as we would like for it to be. And let's see if we manage to obtain something a little better, at least by adding some diffusion term that is controlled by the solution itself. So we would like to use information from the solution to stabilize the problem, and not simply by adding some constant and uniform diffusion, no matter what order of diffusion what order of accuracy the diffusion is. So we have specifically now we are showing this for the advection diffusion equation. The same thing can be applied to system of scalar equation system also of technically the same approach could be applied to the Euler equations and Navier-Stokes equation for the incompressible flows. So we are simply taking a steady state just for the sake of the of what we are showing in this presentation, but it's a steady state advection diffusion equation. It's written in a non-conservative form, so we are not actually going to analyze anything about mass conservation, at least for today. And we simply project it into a proper function space in the usual finite element type of technique. Exactly the same thing is done for finite elements, spectral elements, low and high order. What changes would be how we define the the basis functions, and how we define the grid. So by simply taking a square domain, we subdivide it into some elements, and what we are not showing here would be the possible LGL points for spectral elements, simply because right now there is no difference between finite elements and spectral elements yet. The idea is to show why we need to stabilize Galerkin methods and how we could do it then in a higher order, in a higher order framework. So let's take just an example where we are solving that equation in a square domain, and we fix with Dirichlet boundary conditions a maximum value of 1 of the tracer. The velocity field is skewed with respect and constant. It is skewed with respect to the domain, and is constant in time, and we just advect it. If we simply used this approximation, and we build a linear system that comes out from this with all the type of steps that we need to take to obtain a discretization of the original PDE, what we obtain is this. So it's nothing new. That Galerkin approximation, a straightforward Galerkin approximation, either low order or high order, is intrinsically unstable in the sense of having an unbounded solution. So we would like to at least get rid of and control a little more all these oscillations and obtain something like this that is smooth, at least away from the boundaries, and at least away also from possible internal layers. We will see this image again later with more details, but this is just to give you an idea on where the problem is. In fact, let's take it in 1D. It's the same problem, advection diffusion equation, one-dimensional domain from 0 to 1. And we would like to have an a numerical solution that follows the blue line of the that is represented here, smooth, Dirichlet boundary conditions on the two boundary nodes. The point is that again, according to some parameters, in this case we use a local Peclet number to have a measure on the information of the grid and of the physical problem, and know how the value of Peclet would influence on the stability. So we simply we have two ways of obtaining a stable solution in reality, not necessarily by stabilizing it explicitly with some additional terms, but by, according to a control on the Peclet number, we could decrease the size of the mesh by adding more nodes and still obtaining a stable solution with a larger number of nodes, but without any additional stabilization term. Or we could maintain the same number of degrees of freedom, so having only 5, in this case 5 elements, but by stabilizing the solution in some way and approaching more the exact solution. Of course, the idea is not to increase the number of grid points for obvious reasons, and we need to stabilize it. We decide to stabilize it in some way. Stabilization in the way we want to describe it today is in the same fashion of artificial diffusion or hyperviscosity. There are other ways of stabilizing, to stabilize Galerkin schemes, but we won't go through them. And in this specific case, the idea is to add some term, some viscous-like term, onto the discrete equation and see how to build this term. So in this table, it's actually nice to see a little evolution on how that stabilization term is constructed, going from artificial diffusion or hyperviscosity. We go from artificial diffusion to hyperviscosity by changing simply the alpha. And but of course, this is isotropic. It has the same amount of diffusion all directions. So a very first like artificial viscosity as a Laplacian is not actually used anymore, but yes, it is used in terms of hyperviscosity, so higher order artificial diffusion. That's why we still bring it up today. But maybe a way of improving it could be giving information on the direction on the flow and simply stabilize where advection, in the direction of advection. Still like that, using this method is called streamline upwinding in a finite element fashion. It's way too diffusive anyway. So they started coming out with different methods, of which though finally in '95 the idea of variational multiscale technique was proved to be pretty much the father of every other method, and is a way of having the maximum control over the stabilizing term through the use of information on the equation. In fact, we see in these terms how we go from simply having a diffusion, the Laplacian of the solution in my advection diffusion equation, to having the entire residual of the equation, of the original equation. Well, in this case, we have the time derivative, but for the equation we were showing, we don't really need that. And then some operator, some in this case is the adjoint of the operator. By construction, we can prove how we get to this adjoint, but that's not really the point right now. The point right now is to show how we would like to have a method that can stabilize only in regions where we really need stabilization. And probably the only way to do that is to have an information coming from the physical problem. And the idea, in fact, is it's called variational multiscale. Like many people who don't work in this specific type of stabilization, the term sometimes I notice is not really, like people don't really like it because it's not really a multiscale. In this specific, in the way we are doing it, at least in what I'm showing today, it's a two-scale type of problem. There are not many scales, but the idea behind all this is the fact of using information. Okay, we start from a Galerkin approximation of a differential problem, and we simply discretize it, and we only know what we are doing on the grid points. At the grid points, on every element, we are trying to solve something, and clearly by the examples, we don't have a stable problem. So why is it not stable? Other than mathematically speaking, because we can prove it to be a center type of differencing if we saw it in analogy with finite differences. Well, maybe there are some information we are not considering on scales that are not represented by the computational grid, and so maybe we could try to see how that information can help us improve the solution on the resolvable scale. So that's the idea behind the variational multiscale technique. And to do that, we take the solution, the function space of the solution, and the same thing would be done on the basis functions, on the basis function psi, and we simply split it into the part of the solution that we would always consider in finite elements. So it's a QH in the sense of like H indicates that we are considering the solution on the grid, plus some part that we don't really know. We don't really know we don't know it a priori. We don't know exactly how to build that. We don't know it in terms of function spaces that part of the solution actually belongs to. If we did know that, we wouldn't really, probably this splitting wouldn't really be necessary. Like if we knew what Q tilde, the subgrid scale type of information is constructed and exists in our function space, we could build the function space of the solution or the basis function already considering the way we build Q tilde. Well, we don't know it, so even if This type of technique has been known for the past 15 years, more or less, and even more by considering SUPG, where we have some sort of similarity. We don't know exactly how to model it. There is still research going on, and the most simple, at least to understand and to derive, is what is called algebraic multiscale approximation of the subgrid scale. So, this said, we do some algebra, and by doing some algebra, we obtain exactly that B term that we saw in the table previously. And well, in fact, like this, we already seen that before. With these techniques, or even other stabilization technique, we are able to obtain this. The problem, though, is that BMS, and here the problem of monotonicity. BMS is great in stabilizing where the solution is supposed to be smooth, but the maximum and minimum, although here they are definitely, this is the value here is 1 and the value here is 0 as it is supposed to be, we have under and overshoots. And these under and overshoots, using simply BMS, are concentrated in mostly in boundary and internal layers. We need to get rid of them, and the most straightforward way of doing that is adding one additional term that in this specific case looks exactly like artificial diffusion, although the viscous term is no longer constant and uniform, but it also depends on it takes information on the direction of the flow, it takes information on the solution, pretty much based on the same idea of the stabilization term B, to know where to go and add the diffusion. Practically speaking, this term should be equal to 0 in the part where the solution is smooth, and supposedly that is, like, we are not really adding over diffusion in the middle, but definitely and exactly because that discontinuity capturing as it is designed right now depends on a user-defined coefficient, which is what we don't really want. Maybe we can do a little better on the type of smoothing that we get. So for now, we haven't really seen any difference between finite elements and spectral elements. Like, this is pretty much the same. But we saw how that tau depends on the size of the grid, other than on the flow characteristics. And because it depends on the size of the grid, that's already a problem, because what is the size of a grid when we are talking about spectral elements with internal nodes that are not equispaced, and other than the fact that the grid might even be not uniform. So because of the variation, because it's not that clear yet how to define that tau that depends on h, we still might get problems as we go higher in the order of accuracy, which is exactly the case when the LGL points get even closer to each other on the boundaries on the element. So if everything worked perfectly with VMS and discontinuity capturing using linear finite elements, when we go higher in order, in this case we are at it's an 8th order simulation of this advection, pure advection problem with an L-shaped discontinuity, still we get, if not anymore on the internal layers, as actually the discontinuity capture term should well avoid, but we still have in certain specific and singular points we get still a problem. So for now, maybe as long as we are happy with having under and overshoots on the order of a few percent points, that's all fine. Maybe that could be acceptable. However, if we want it to be completely smooth, then maybe one idea, which is actually used by others, or limiters do act in a similar way, is going down to first order only in certain regions, in the regions where we have the discontinuity, which in a way is like going, okay, I go to high order, but then I need to go lower in order. So there is work to be done on trying to avoid this technique and using VMS and define tau so that the solution is smooth enough also on the discontinuities. Yes, we have what we call it first order subsets, FOS. Definitely it improves the solution. Clearly we go down to first order. We are adding some artificial diffusion, not really artificial diffusion, but let's call it like that just to generalize it. So yes, the solution is positive, but then we lose in accuracy. What is nice, well, here is just an example on exactly on that problem. It's actually clear in here. This is a close-up of that. So we cut that L-shaped solution with a plane, and we obtained a VMS solution. We said that where the solution is smooth, VMS acts pretty well. So as long as we are far, we get away from the discontinuity, the solution is smooth, and in fact we don't see actually the red line anymore. It's covered by the smooth solution. But we still have these undershoots here. So we improve it by discontinuity capturing. If the problem is 8th order, where maybe 4th order, the undershoots using discontinuity capturing wouldn't be as pronounced, but still it would probably exist. So we haven't solved that yet, and that's when, by going down in order, only where the discontinuity appears, we finally get a very smooth solution, and at least it seems to be quite accurate. So it's not over diffusive, but at the same time, but is not does not maintain the order of accuracy of the underlying method. What is nice though about VMS by itself, although we have some problems, clearly on discontinuities in terms of undershoots. What is very nice is that it maintains the order of accuracy. So if we solve the same problem simply by using filters, 4th order filter, the accuracy goes down, and so does for 8th order filter. So the convergence rate goes down to almost 6 and to 3, one order less than what is expected. VMS apparently behaves well, and doesn't affect at all in this under this condition. Now finally, and we're almost done, but up to now all these problems were very simple, were relatively simple. It was uniform velocity field, everything constant. So let's see what happens if we put the tracer in a problem that is either more related to what atmospheric simulation would be. So we have a thermal, and here's a warm bubble that we start rising. So this problem is solved. We are not stabilizing using VMS the dynamics, but yes, we are stabilizing using VMS the tracer. But the tracer is superimposed to the thermal, and so it should follow the thermal closely. In fact, it does, but the filter, as we saw in simpler problems, we couldn't expect on even more challenging problem to avoid any type of oscillations in the middle. We have under and overshoots, and not only close to the boundaries. But that's what we can achieve up to now, unless we use some sort of limiters and classical limiters that still are used and apparently quite efficient by the point of view of the people who use them. So artificial diffusion it's crap, because crap in the sense that since we don't really have a control on the diffusivity term, and we just put 1 here, now I can explain to you why the 0.001 where it comes from, but we just select a certain diffusivity coefficient, and well, we get what we get. It's way far away than what we would like to have. So VMS BMS definitely. We were hopefully expecting to have a smooth solution in the internal region, and good enough we do. But yes, those undershoots are here, even if I can't really explain what this type of oscillations in this region here really mean. I'm not really sure, but the solution acts pretty well up to adding a shock capturing. So this is simply to show how the method is not designed only for simple problems, but apparently we can try to approach some good results also in this case. Actually, this problem is not really, it's 2D, but in reality was run on a periodic domain in the y direction. So it's actually it's an infinite cylinder in this specific case, but that doesn't really make any difference on the method itself. And just to give you an idea on the improvement on the error, depends what we consider high error, large error in terms of under and overshoots, but definitely we are way below the problems, the type of error that we would get using other type of this is just an error on the maximum and minimum values with respect to the nominal maximum and minimum. So definitely an improved solution. So we can improve positive preserving, even if we need to say that by using the discontinuity capturing, we would go down, the actual order of accuracy will not be the same of the spectral element method, which is, however, the case of using BMS. So BMS preserves the accuracy that we would like, the numerical accuracy that we would like to have, and it avoids all the oscillations in the smooth part. Up to now, the problems were either steady or a steady state, and even when they weren't, we used very small time steps. It was fully explicit with very small time steps, so that when we derive, we haven't seen it here, but there are papers to actually see that when you derive your BMS formulation, you have some time derivative of the sub-rescale variable, and in this case, all these time derivatives were set to 0, and I could do that because of the small time steps. Otherwise, I would have to see how to consider. We would have to include in some way those time derivatives, and yes, and if we really want it to be smooth enough and fully monotonic, well, the first order subsets would be what helps VMS in the task. So, and this this work actually just came out in a paper last month, and but all this theory was developed starting from 1995, and except for the discontinuity capturing that is actually older because it's related to the use of SUPG rather than VMS in the past, and that's pretty much it.
Other questions? I have a question.
Yeah.
With the artificial viscosity, have you ever tried to choose a viscosity parameter that is proportional to the gradient of the wind speed, for example?
No.
Okay.
No.
Because I would like to see how that performs.
Yeah.
Joanna?
I'm not sure if I got it correctly, so please correct me. Are you saying, because it appeared to me that you may be concerned that you are lowering the level of your solution at the very discontinuity of the shock?
Yes.
Actually, because I come from aerospace engineering, when we are happy when we have a lower, well, if you have a formal shock, we would like to have a higher order solution near the shock, and we
But
are
not
happy
at
to have a lower. We believe that this is a correct way, because you can't really say what is at the discontinuity, that your equations are not formally valid there.
Right.
So, am I correctly thinking that you are striving for something which...
Yes, in a way, yes. It's simply like I don't know how those convergence rate curves then would behave in general in the global.
Again, both in aerospace and recently I did hydrocodes type of work as well. When we have a shock waves or other strong discontinuities, then the mesh convergence studies are not valid anymore. So
Right,
if
yeah,
you are
because exactly because
concerned
it's discontinuous.
yes,
So,
so you
yes.
can still show some tendencies for the first order things, but you would not. So we usually don't
Worry about
anticipate to have a formal mesh convergence if you
Okay.
have this type of features, because mathematically they are not,
you
not
don't,
perfect.
you can't expect.
However,
Yes.
the difficulty is, because we use various forms of either smoothing gradients or whatever it is, the true difficulty is to know where the shock is.
Right,
Your
yes,
solution
in
can
fact-
be solved and you can do the trick.
Yes, yes. Like here,
So
this.
this is, you know, if you have a 3D thing with lots of shocks interacting, you have no idea where to put
Yeah.
it. So pressure switches are too primitive usually to do it as well as we would like.
Yeah, where in fact the quality error estimator here was simply looking where the gradient is large.
Yes, so you
but
have a gradient
there
of
should
pressure
be-
switches, that's the usual way
yes,
you
yeah,
do it.
like
But
if you wanted to do it more,
so there is a
Correct.
research to find where to have a shock, but everybody is happy with they
With the
actually
order.
think that it's good that you drop
the order, yes.
if you
Good,
are
good,
able
good
to
to-
drop
Good,
it
good, good.
in the correct place,
Thank you.
if it helps you.
Yeah, thank you.
Other questions?
I'd like to add to this. It happens in literature every once in a while, but the whole concept of the order of convergence is directly related to Taylor series expansion. And if there is a discontinuity somewhere, all derivatives won't be function, will be some deltas, right? So the concept of order of convergence does not exist for this continuous solution. This is it.
Yeah, yeah.
So if you see some improvement in convergence, it's when you are converging to some solution which is incorrect. It's not the solution of your problem.
Yeah, yeah, I see.
Your last example was for a smooth solution, right? The eighth order convergence.
Oh yes, that was a smooth. Yes, yes, that was the smooth bell.
It was just to show that you weren't sacrificing that.
Yes.
This one.
Yeah, it's the smooth solid body rotation.
Further questions? Seems not to be the case. So let's thank Simone again.